All right, let's just jump right in and talk about the fundamental language of the web, HTTP, the Hypertext Transfer Protocol. It is, quite literally, the engine running under the hood of every single website you visit. So here's the thought. The entire modern world, everything you do online, it all runs on a conversation that started way back in 1989. Every time you load a web page, you're kicking off this very specific, very fast conversation. So what are your browser and the server actually saying to each other? At its heart, the basic idea is, well, surprisingly simple. Your browser, the client, uses DNS. You can think of that as the internet's phone book to find the server's address. It opens a connection, sends a GET request asking for a file, and the server sends it back. Then, connection closed. Simple, right? But that kind of simplicity was never going to be enough for the modern web. Yeah, that basic back and forth was totally fine for, a single text document. But for the web we have today, with images, videos, scripts, and hundreds of files per page, that conversation had to get a whole lot smarter and a whole lot faster. And you can really see that journey laid out here. We started with the super basic HTTP/0.9, then versions 1.0 and 1.1 came along, adding more features, trying to make things a bit more efficient. But the real game changers, HTTP/2 and HTTP/3. These weren't just updates. They were radical redesigns built for the insane scale of today's internet. So let's talk about those growing pains. The crucial problem with HTTP 1.0 was just how ridiculously inefficient it was. Seriously, imagine having to hang up and redial the phone for every single sentence in a conversation. That's exactly what your browser was doing for every single image on a page. It was a crawl. HTTP 1.1 introduced Keep Alive, or persistent connections, which was the first real fix. It let the browser just hold the line open and request multiple files over that single connection. But even a persistent connection has its limits. A modern web page isn't 10 files. We're talking hundreds. And trying to shove all those requests down one pipe, one after the other, well, it creates a massive traffic jam. That's where HTTP/2, which actually grew out of Google's SPDY project, comes in. It introduced multiplexing, which let dozens of parallel requests and responses happen all at once over a single connection. It was a massive leap forward. Okay, now this is where things get really radical. HTTP/2 was fast, for sure, but it was still built on TCP, the internet's super reliable but also super old transport protocol from the 1970s. So HTTP/3 did something kind of nuts. It threw out TCP entirely and replaced it with a brand new protocol called QUIC. I mean, think about that. This isn't just an update. It's changing the fundamental transport layer of the web for the first time in over 40 years. And this is where we are today. The new protocols HTTP/2 and 3, they absolutely dominate, handling over 95% of web traffic. But you see that little 5% slice for HTTP 1.1? It's still hanging around. Why? Because on the internet, backward compatibility is king. So we've covered the evolution of how the connection is made. Now let's dig into what is actually being said in this conversation. The client's request starts with a verb or a method. Most of the time, you're just using get to, well, retrieve a page. When you submit a form, you're likely using post. And put and delete are pretty much exactly what they sound like. They're direct commands to modify or remove data on a server. The server's reply always starts with a 3-digit status code. It's a super quick way to know what happened. Anything in the 200s means success, you're golden. 300s are for redirection. 400s mean you, the client, messed up. Yup, the classic 404 not found lives here. And 500s mean the server itself is having a bad day. It's a clean system for diagnosing what went right or wrong. Now, it's really important to realize this conversation isn't always a direct line between you and the web server. There are often these, let's call them middle managers or intermediaries in between that play some crucial roles. One of the most important is a caching proxy. Think of it like a local library. If 100 people ask for the same popular web page, the proxy keeps a copy nearby and just hands that out, instead of making the main server do the work 100 times. This is a massive reason the web feels as fast as it does. Then you have gateways, which are essentially translators. For example, a gateway can take a modern HTTP request and convert it into a completely different protocol, like the old file transfer protocol, or FTP, to communicate with some ancient server. They bridge the gap between different systems. And finally, there are tunnels. These are the simplest intermediaries. They just create a secure pipe and pass data through without inspecting it at all. VPNs and firewalls often use tunnels to relay traffic. They're just blind, secure couriers. Of course, none of this speed or complexity matters if the conversation isn't private. And over the years, we've had to build some critical security layers right on top of HTTP. I mean, you see HTTPS everywhere now. That S means the entire conversation is encrypted. But there are other key pieces. HSTS tells your browser to only talk to a site over a secure line, no exceptions. And CORS is a set of rules that prevents a malicious website from, for example, using your browser to make requests to your online banking site. These are all essential parts of the modern security stack. So let's pull all this together. We've traced the path from a dead simple text retrieval system to the complex layered protocol that powers our entire digital world. And the crucial takeaway of the latest evolution is this. HTTP/3 isn't just a tweak. It's running on a complete replacement for TCP, a protocol that's been the bedrock of the internet for 40 years. That is a fundamental, seismic shift. And that really is the whole story. What started as a simple request for one file has become this sophisticated, multi-layered, secure conversation that's constantly being re-engineered for the demands of the modern web, all running on a brand new foundation. So that leaves us with one final question to chew on. We've engineered our way around inefficiency, concurrency, and transport layer bottlenecks. The protocol has been rewritten again and again for speed and complexity. So what's next? What's the next big problem that will force us to reinvent the language of the web all over again?